Hey everybody, it's Ribley back again. We're going to do a quick little review of what an inverse function is and the properties of inverse functions. Excuse me, and then we're going to talk about logarithmic functions because I know you saw them back in Algebra 2, and I also know that you play with them a bit in pre-calculus, but I definitely want to make sure that you have some skills when it comes to the logarithmic functions and just logarithms in general, okay? All right, so first things first, let's talk about inverse functions. Remember the notation for a function is f inverse of x. All right, so really simply, I'm not going to get nutty with this. If I have f of x is equal to 2x minus 3, and I want the inverse, I would simply, hopefully you recall, remember y equals f of x. So I would simply take the x, or excuse me, take the y, turn it into the x, take the x and turn it into the y, and I would solve, and I'd get x plus 3 halves equals y, and this is f inverse of x, all right, with respect to this function. Now, it's still a function, right? Remember, if the function is going to have an inverse which is also a function, then it has to pass the horizontal line test, which implies that it has to be 1-to-1, which implies that for every y, there is only one x that goes to it. Those should all be terms and terminologies that you understand and have heard, okay? All right, cool. For example, just really quickly, if I have, let's see, y equals x squared, this is y equals x squared. This does not pass the horizontal line test. If I pick y equals 4, there's going to be x equals -2 and x equals 2 that maps to it. And that simply tells me that its inverse, which we know the inverse of the square root of x, or excuse me, of x squared, is y equals root x, right? But it can't be a function, because if I wanted to graph the whole inverse, this guy's not a function because this guy's not 1-to-1. Again, I'm blowing through this relatively quickly, but I want to make sure that we understand what's going on. All right, there are graphical ramifications of functions and their inverses, the not least of which is, remember, the way in which I create an inverse function is by switching x and y. And what that does graphically is it creates the phenomenon wherein if I have a function, let's say that this is f, all right, it is going to reflect, its inverse, excuse me, is going to be reflected across y equals x because I flipped them, right? They became, and oh, let's see if I can do this properly. Ah, that was terrible. Sorry, that's a little bit better. So this guy would be f inverse of x. That's the graphical ramifications. Functions and their inverses are reflected, excuse me, assuming that their inverses are functions, are reflected across y equals x. Even if they aren't functions, but see, I was a little glib here because I said f inverse of x, so I presented it as a function. Even if the inverse, as in this case, isn't a function, it's still reflected across y equals x. Here's y equals, I'm gonna butcher this. Sorry, my hand was in the wrong spot. These two curves are reflected across y equals x. All right, the algebraic ramification of functions and their inverses is this guy right here. If I compose f with its inverse, and I can do it in either direction, f inverse of f of x, so I'm composing f with its inverse in both directions, I always get x. So that's one way that you can always check to see if a function, if an inverse is in fact an inverse of a function. All right. So last but not least, let's talk about this sort of in set notation. If this is my domain and this is my range, and f sends values of x, if I have an x1 here, this thing gets to, this is f, to f of x1. If you think of this in set notation, what we do is if you now hand me, if this value is my new x, I'm going to call this x1 prime for lack of a better word, this thing will get mapped back to f inverse of x1 prime, which is equal to x1. Okay? In other words, inverses, are the functional equivalent of undoing something. Now, if you didn't have me before, if you haven't had me for classes before, if you think of, if I try to solve 2x equals 10, then the multiplicative inverse is not dividing by 2, it's multiplying by the reciprocal, right? Which I know you're going to say, Ripley, it's the same thing. Careful. It's easier algebraically to think of multiplying by 1/2. So multiplying by 1/2 undoes 2, right? It turns it into the multiplicative identity. 1 is the multiplicative identity. If I multiply anything by 1, I get the thing back. If I multiply through by 1/2, these cancel, and x equals 5. Multiplication by the reciprocal is the multiplicative inverse. All right, if I have x plus 5 equals 17. Now, the additive identity is 0. If I add 0 to anything, I get the thing back. The additive inverse is to add the negative of the value. All right, you say, but Ripley, that's just subtraction. Well, careful, there's no such thing as subtraction. It's adding with a negative, right? This guy cancels and becomes a 0, just like this guy canceled and became a 1. In this case, whoops, x equals 12. Well, when we got into functions, mathematicians were like, wait, whoa, what is the functional equivalent of an additive or a multiplicative inverse? Well, it's this guy right here. If I compose, if I want to make, in this case, if I want to make f disappear, what I do is I compose f with its inverse. These guys, quote unquote, cancel, and out pops x. Likewise here, if I want to make an f inverse disappear, I compose it with f. These guys cancel, and out pops x. All right, which is the functional identity. You hand me a number, I hand you the same thing back, right? Think of y equals x. If you hand me a 2, what am I going to hand back to you? Whoop, you get your 2 right back at you. All right, just like when I multiply by 1, I get the same number back. If I take a number, multiply by 1, get the same number back. If I take a number, I add 0, I get the same number back. If I take a number, I stick it into y equals x, I get the same number back. So these things aren't happening in a vacuum independently of one another. They're not mutually exclusive events. What they are they're all combined, and they're a continuation of one another. Okay? All right. Enough. Ripley, shut up, for God's sake. All right, now that we have an understanding of what an inverse function is, let's talk about y equals the natural log of x. And this is where everybody gets a little grip. They're like, oh, Ripley, I hate logarithms. Well, let's look at the function real quick. I know you've already seen it. Don't get annoyed with me. Just simmer down. Remember that the natural log of x is the inverse of y equals e to the x. So it's real simple. Here's y equals e to the x. This is y equals e to the x. This guy has a horizontal asymptote at y equals 0, and it passes through the point 0, 1. Right? Now, if I want to do the natural log of x, remembering, of course, that these guys are inverses of one another, it's super simple. All I do is I turn my horizontal asymptote into a vertical one. I turn the point 0, 1, since all I do is exchange x and y. This becomes 1, 0, and bam, off we go. And even with my cruddy drawing, they're still symmetric about y equals x. That's pretty awesome, isn't it? Now, this is just the mother graph right here. F of x equals the natural log of x. So it behaves like all other mother graphs. If I want to move it around, I'm not going to bore you with this, but if I take the natural log of, let's say, x minus 5, and I say plus 2, right? Now, remember, let me back up just a titch. Look at y equals e to the x. I know that the domain is all reals. I know that the range is everything. Let's write that down. Domain is -infinity to infinity. I know that the range is from 0 to infinity. All right. I may have mentioned that in the last video, but I kind of assumed that you knew that. If I assumed incorrectly, I apologize. Well, just look at f of x equals the natural log of x. I mean, you can look at it, or you can realize that if x's and y's change, the domains and range change as well. The domain of this guy is from 0 to infinity. Not only because you can look at the graph and see that that's true, but you also know that the range of e to the x, excuse me, is 0 to infinity. The range goes from -infinity to infinity, which is pretty rad. Okay? All right, now let's talk about laws of logarithms really, really quickly. Let's understand a few things that are super important. But I wanted to make sure we had a little quick review, maybe inspire you to remember some of your stuff from Algebra 2 and from pre-calculus. First things first, I know if y equals a to the x, now I'm saying it can be anything, then y equals log base a of x is its inverse, which implies a to the log base a of x is equal to log base a of a to the x, which is equal to x by this property right here. All right? That's the key. We've defined logarithms by virtue of their relationship to their exponential functions. That is, they are inverses. Okay? Easy. Excuse me. I had to give myself a little sip. Okay, excuse me. Now let's talk about properties. And you've seen these before and you probably panicked, but remember there's only 4 of them, which is awesome. It's the magic number, other than the inverse property, which isn't really a property, it's a definition, right? Excuse me. So here we go. Property number 1. I know that log base a of a product, let's say u times v, is equal to log base a of u plus log base a of v. Now, hopefully you were shown that the reason why this happens is because we know that a to the u times a to the v is a to the u plus v. That's where this property comes from. Similarly, since a to the u divided by a to the v is equal to a to the u minus v, and I'm being a little glib. I'm hoping that you've seen these proofs before, but this is not an Algebra 2 class, so I'm going to assume, all I'm trying to do is inspire your memory. This is u vths is equal to log base a of u minus log base a of v. All right, that's pretty key. That works out pretty nicely. Number 3, I know that, whoa, I want to mention this. I want to mention something really quickly, and I'll do it in red pen because that's the color of the pen that's going to be used if you make these mistakes. Log base a of u plus v or log base a of u minus v, you're stuck. We don't have a property for these. Okay, we do not have a property for these. So you're stuck. That's all you get. You can't putz around with these things. Okay, so I've waved my hands and I've warned you off, hopefully. All right, last but not least, log base a of, excuse me, of u to the c is equal to c log base a of u. Now, this one, I can wave my hands and do a proof of this, because if you think of u to the c as u times u times u times u c times, then I would simply be doing log base a of u plus log base a of u plus log base a of u dot 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 c times. So if I do that, I just end up with c log base a of u. Okay? Now, last but not least is the change of base formula, which is my favorite. I know that log base a of u can be written as log, I'm just going to do log, the common log, log base 10, of u divided by log of a, or log base 2 of u divided by log base 2 of a, or the natural log of u divided by the natural log of the natural log of a, thank you. And this can be written in general form as log base b of u divided by log base b of a. Now I'm going to prove this one. It doesn't take very long. I can blast through it pretty quickly. All right, and then we'll be done. There's nothing more to this. Okay, pretty straightforward. But I do want to prove this. So suppose that let's see, where should I prove it? Let's do the proof up here. I don't want to burn a whole another page. Let's do the proof. I don't know why. I'm being lazy apparently. All I'm going to do is I'm going to let log base a of u equal question mark. Now, we know by the definition of logarithms that this can be written as a to the question mark equals u. Remember, that's where this is the relationship between logarithms and exponentials, which is it's a handy-dandy little thing. All right, now I'm going to, so I got a to the question mark equals u, and you may be going like, Ripley, how does that help? Well, watch. I can do whatever I want in algebra, right? I can do whatever I want in an equation as long as I do it to both sides. So I'm going to take log base b of a to the question mark equals log base b of u, right? You with me? Now remember, at the end of the day, I'm trying to solve for question mark. Well, property, this lovely, delightful, delicious property number 3 that's sitting right here tells me that if I've got log base b of a to the question mark, I can write that as question mark log base b of a, which equals log base b of u. Now, remember, this is an ugly number, but it's still just a number. I'm not afraid of it. Just think of it as, I don't know, 17.9236125, right? Who cares? It's a number. I'm trying to solve for question mark. So this is akin to solving for 2x equals 10. I'm just going to divide through by 2. I'm going to multiply by the multiplicative inverse, which is the blah, blah, blah. Anyway, so question mark is equal to log base b of u over log base b of a. And we are done. We'll give it a little smiley face, which is this guy right here. Now, the cool thing about this is, and the reason your calculator only has 2 logs on it, if you look at your calculator, at the face of it, it's only got a common log, which is log base 10, which is just log, and it's got the natural log, Logarithmia naturalis, right, which is ln. Because even if I'm in log base 93 and I'm trying to figure out log base 93, oh man, I don't want to start a new page. I'm being lazy. So log base 93 of 152, right? 93 raised to question mark is going to be 1 point something, right? You agree? But my calculator doesn't have a log base 93 on it. Well, I'm not afraid. I would just go natural log of 152. Whoa, that was cool. Sorry, of 152 divided by the natural log of 93. It's going to spit out a number. Just throw it in there, and you'll end up with a number around 1 point something. All right, cool. Again, a review. All right, I blast through these things, and sorry I was a little bit lazy with using my next page. They're just precious. I like my pages. See, I would have hated to just use a little bit right here. Anyway, thanks for your time and attention. Thanks for listening. I hope it was helpful, and I'll see you soon.